All right, so I want to begin by actually talking about the recursive code that I have given to you in the latest Codio unit. And as we discussed towards the end of last class, it was printing all subarrays. What I've specifically given, and it's basically the same idea, is printing all substrings. Okay, so what is a substring? So if you take a substring A, B, C, D, so this is your string. Substring is any subset of the positions, right? Any subset of the positions, and you put them in order. So you have, in this case, this is of length 4, and so you will have 16, which is 2 to the 4 different substrings, one of which is the empty substring. So there's the empty substring, then there's A, B, C, D. Those are the ones with, so there's sort of the empty substring over there, A, B, C, D, then there's A, B, A, C, A, D, so on and so forth. So what I have given is a recursive code to generate this, and I want to discuss that recursive code. And then in the unit, I've also given code that does it using stacks. Okay. So let's, and again, I'm going to use a sort of pseudocode-ish syntax, just so that I get the ideas across. You know, I might make syntax errors, so don't get caught up in that. I have given you the code. So let's just say I have this function void, and I'll say print all substrings, and I give it as input some string s. Okay, so I'm going to think of my string. So here's my string s. So what is the logic? Okay, so are there any questions about the question? Do you understand what I want you to do? What this function is supposed to do? Good. So I'm going to define a recursive function that does this. And you'll see that actually, if you think about it, it's very hard to do this with iteration, with while loops. Like, how would you do that? Because if you think about it, the number of nested loops you need is actually the length of the string. So I'm going to write a recursive function.
Professor?
Yes?
Could you focus the camera? People are saying it's blurry, and it's blurry from my end as well.
Is this better?
It's just pretty much the same.
It's pretty much the same.
I think we went over this last time. It's the same problem. It's probably not going to be fixed.
No, when you started the class, everything looks really nice, and then it just became like that.
Yeah, let me see what I can do here.
I think our resolution for this last time was physically moving it closer and just moving the page around more frequently.
Sure. Let me see if let's see if this works here.
Yeah, that didn't really help much last time, though.
Making everything larger?
Yeah, it's still blurry. Larger blurry is still blurry.
Is this better?
Yeah, that's great.
Oh,
that's clear. That's super clear.
That's perfect.
Okay, so it's strange. I mean, I'm actually taking the video feed from my local recording and actually piping that to Zoom through screen share.
And that's better?
That's way better.
That's what I did last time as well, and that didn't work. So it's very strange. Okay. So let me know if
Yeah,
this is working.
it's laggy.
It's going to be laggy, but it might be clear. So that's the trade-off, unfortunately. Sorry.
Trade-offs.
Yeah. But is it clear now? And can you hear me clearly?
Yeah, we can hear you, and it's super readable. So
Okay,
I think
good.
the frame rate is fine.
Okay. So I'm going to create another function. This is the recursive function that I'll call the input string and the fixed string. So the way this is going to work, the way the recursion is going to work is, here's how I want you to think about it. So here's my string s. Some portion of the string, this is going to be the input string. A subset of this subset or a substring will be the fixed string. So the idea is that fixed string is only going to be some subset of these positions. It's going to be a substring. In string is going to be the prefix. So you can think of this as the prefix, and this is going to be a suffix, but a subset of suffix, not the entire suffix. And what I'm going to show you is how you can make recursive calls to this function to print everything. Okay, so let me sort of maybe even explain this a little bit more. So the base case is we'll say when the input string is empty, this is going to be the base case. What we'll do is simply we'll print the fixed string. Now the recursion is going to take this character here, remove it from the in string. So the input string is going to go down. And then it's going to make two recursive calls, one in which it adds it to the fixed string and one in which it doesn't add it to the fixed string. Okay, does this make sense? So this is going to make two recursive calls. Okay, so let me refer to this part as foo. This character is C. There is going to be one recursive call for foo C plus the fixed string. By plus, I just mean like appending it, right? Appending this to whatever is fixed. The second call is going to be for foo fixed string. Those are going to be the two recursive calls that are made. Any questions? Does that make sense?
Professor, could you please explain why you decide to divide the host string into the input string and fixed string?
Okay, good. So why am I doing it this way? So let's go back to saying how to generate all substrings. So one way to think about this is for each character, it is either present, like in the substring, like it's either present in the substring or not. Right? That's really, if you were to think about how are you going to generate all possible substrings, you could look at each character one by one and say, okay, I'm going to keep this, I'm not going to keep this, I'm going to keep this. For every possible choice, you will get a substring. Okay? Does that make sense? So you could go through this, and for every character in here, so you look at it character by character, you choose which ones to keep and which ones to not keep, which are present and which are not in the substring. And this is the process that we need to simulate through recursion. So the way it works is each recursive call is looking at a particular character and saying, do I want to keep it or not? This is keeping it, this is not keeping it. So I keep track of whatever has been kept, and I'm keeping track of the things that I still need to make decisions for. Does this make sense? Questions?
Yes.
So the recursion is basically deciding whether to keep the last character in the input string. And the fixed string,
Professor?
yeah?
Given a string n,
how many recursive calls will this program do?
Good question. So let's come to that shortly. Let me first write this out, and then I will come to that. That's a good question. So the fixed string keeps track of all the characters, that are kept. Okay, maybe it keeps track is like it tracks. I don't want to overuse, I don't want to overload the word keep. So deciding whether to keep the last character in the input string. So you're deciding whether you want to keep this last character for the substring. And so fixed string just keeps track of all the characters that have been kept. So this is going to keep the character C, and this is going to not keep. It's going to drop the character C. So let me just write out the recursion. I'm going to write it out in a sort of pseudocode-ish way. So I'll say void print all substrings. So there's a string which is the input string, and then the string which is the fixed string. So the base case, I'll say that if the length of the input string is 0, and if you're in C, you can do like the string dot len or whatever. So I keep switching between, for strings I end up switching between Python and C++. It's not important. You'll see the C++ syntax there, but you get the length, and you say if the length is 0, then you can print the fixed string and return. Right? So this is the base case. This is the base case. On the other hand, so now we actually do the recursion. So we'll say let the character C be the last character of the input string. Okay, so there's in C++ you can get a function that would get this. Then you in string is equal to or I'll write it out sort of in English, and then you'll see. Or I'll see. Delete the last character from the input string, because you've made a decision on that character. You've made a decision on C, so you remove it from there. And again, there's a C++ function. It's called popback, which you can call to do that. And now you make your recursive calls. Right? So you can make one recursive call, which is just going to be print all substrings of the input string. I'll say C plus the fixed string, and you can do print all subarrays of the input string and the fixed string. Okay.
Just a quick question.
Yes.
C plus fixed string just appends.
It's just appending.
The beginning.
Yeah.
Okay.
Just appending.
Professor, I have a question.
Yeah, go ahead.
So means when we use the C letter, means the last letter of in string, do we add that to the fixed string later on, after we are done with all those two recursive calls?
No, at this point it ends. There's nothing to be done.
Okay, got it.
It doesn't really matter at this point, because at this point the printing has been done. Right, so you should think of this as this is passing by value, not passing by reference. Right, if that is sort of, but in any case, I'm not really modifying fixed string. I didn't want to modify it here because I'm going to call it on fixed string. You could flip these lines and you can do whatever. So actually at this point, I want to poll you. I want to ask a question. Let me see if I actually have access to my questions. Okay, I do. Okay, so here is the first question. So here's the piece of code, I want you all to be able to see this. So is this clear? Can you guys read everything?
Yeah.
Yes? Okay, good. So everything, okay. So here's my first question. Well, okay, so before I get to the question, and then, we have this dummy function which just does the top level call, right? So if I do void print all substrings of some string, which I'll just refer to as the input, then I will just call print all substrings of what? Like, what are the arguments going to be now? Remember, I have to call this function. It has two arguments. What should the two arguments be?
Inputs and an empty string.
Exactly. So it's input and just the empty string. Okay, this is the empty string, right?
Is that what fixed means? Empty?
No, so fixed doesn't mean empty. Fixed starts off being empty, but during the recursive calls, it starts accumulating more and more characters.
Okay.
So here's my question. Now that you have this, okay. So here's the question. So this is when you make this call. So when you call this, which is the first substring printed? So your options are the red option, as I used to have it, is just the input. So I'm making this function call, right? I'm calling it on the input, and it's going to call it on some substring. The substring could just be all of input. Is it the empty string? Or is it something else? So I'll just launch the poll. So this is the question. Is it the input? Is it the empty string? Or is it going to be something else? I'll give you a few minutes to answer that question.
Can you repeat the question?
Sure.
Oh, sorry. It's written, right?
Yeah, it's right there.
Okay. My apologies.
So I'll give you a minute to think about it. I'm just going to move this a little bit further down so that you can see everything. Remember, this function call, that's just the declaration. Maybe I can go up a bit more so that you can see it, everything. Okay. So I'm going to end the poll now. And it's split between all the answers, but more people gave the correct one, which is it's the entire input. It is the entire input. Now, why is it the entire input? If you look at the very first recursive call, the first recursive call takes the last character of input and adds it to the fixed string. That recursive call is going to go back, and the first recursive call that it makes is just going to take the second last character and append that. And if you trace this all the way down, because this function is called first, it's the input, which is the very first string to get printed. The empty string will be the last string to get printed, because that would be the second recursive call, which makes itself call itself recursively. Now, someone asked the question of how many recursive calls are made, which is a good question. So how many recursive calls are made? How many recursive calls if input has n characters.
N, right?
That's the depth of the recursion.
So 2 to the nth power, same as all the substrings number.
2 to the n minus 1.
It's yeah. So it's basically it's technically it's 2 to the n plus 1. I mean, I should check. So essentially it's 2 to the n. It's not exactly 2 to the n. It's a little bit more because there are intermediate calls being made. The reason why it's 2 to the n is, think about it, that in the end, every single substring is its own base case. Every single substring is its own base case. Right? And that gives you the 2 to the n. But then there are other intermediate non-base case calls that are made. So if you want it to be precise, then you would get this. But 2 to the n is basically what I was looking for. Right? So there are 2 to the n. And as for this, you'll have to work out, there's some math to be worked out, but it's basically 2 to the n. So exponentially many calls, which you expect because there are exponentially many substrings.
Professor, can you elaborate on what you mean by every substring is its own base case?
Sure. So let's look at, this string A, B, C, D. Okay, let's say this was the input initially. Now, eventually, this algorithm or this code is going to print every substring. So how many substrings are there? There are 2 to the 4. There are 16 substrings. And you can ask, when is this going to be printed? Eventually, there's going to be a print command to the substring. The print command is part of the base case. And this only prints one string. So every base case is printing a different substring. And there are 16 substrings, so there have to be 16 base cases.
But it only prints if length is equal to 0, right?
It only prints. The list is empty? It only prints if the input string is equal to 0, but it's printing the fixed string, not the input string.
Oh, okay.
So eventually, for every substring, the input string will eventually become 0. So what I highly recommend is, I have given you this code in the Codio unit. First, understand how this code works. Now, when you understand how this code works, there's also a stack-based implementation of this recursive procedure. There's a stack-based implementation of this code, which is also there in that unit. For the second test, you are going to have to give a stack-based implementation of some different functions. And I've written the function. So the second test, I've actually told you exactly, I've given you the entire setup. So I don't want to go into it right now. I want you to go look at it. And on Tuesday, when you have questions, you can ask me next lecture. The important thing for you to do now is, okay, so now assuming that, you of course you're working on linked lists. The next thing is to work on stacks. But before you work on stacks, I want you to understand the recursion here. When you understand the recursion here, then understand how the recursion is simulated through stacks. It's very similar to the last lecture, where there's a pop and then there's a pushing in of 2 calls. It's the same logic. And you'll see the stack-based implementation. And once you understand those, you'll be set up for the second test, and you will understand the stack-based recursion pretty well. I will take a couple questions at this point before moving on to the next topic. Yes?
Regarding the input for print all sub, shouldn't the quote space quote be the first parameter and the second one just be a fixed empty string when you're calling
what I'm calling
the bottom
this?
Of your paper?
No, actually the first argument is the input. The second argument is the empty string. The first argument is actually going to be that.
The question is, what is defined as that input?
I'm sorry, which one? This one?
Yeah.
This is just doing, like, this is like a dummy call. This is just, or rather, this is the dummy call. This is calling the recursive function with the right parameters? Maybe I'm missing the question here. I don't understand. Maybe. So, like, okay, so this is the non-recursive function that actually prints all the substrings. That is going to make, it's going to call the recursive function, right? We're overloading with with this function with other arguments. The first argument is just the entire input string. That's just the entire string. The second argument is empty. That's the empty string, because the fixed string is initially empty. And then as the recursion progresses, more and more of it gets fixed. So the input string is going to keep shrinking each time because you keep deleting the last character. Every time there's a recursive call, you delete the last character.
The exact question word for word is, shouldn't in string not get passed in, but instead an empty string on the second call to print all sub?
In this one? In this call, I'm assuming that's the call.
Perhaps, yeah.
No, the input string will always stay the same. Okay, let's go back to the previous picture that I had. Let me see where, here. Remember this picture, right? So what did we say? We said we took the character C, we added it to the fixed string, or we don't, but foo is the same. Because this is the portion that has not been fixed yet. So the portion that has not been fixed stays the same in both calls. It's the portion that's, or rather it is what has been fixed that is different in these calls. The portion that has been not fixed, I'm sorry, the portion that has been, the portion that is not fixed is the same for both calls. So please ask more questions at this point if this is not clear.
So I have a question. Can you go back to the code? Yeah, here, the first call, the first recursive call, you append the string and you keep doing that until you get all the string, until the in string is empty, right?
Correct.
And that prints the fixed string.
Correct.
And then this,
it prints the original. I'm sorry, it prints the original input.
Original input.
Yes.
And then when it goes back and calls the second recursive function, over here, in string is still the input and fixed is empty.
No,
or fixed
remember
is with one character.
These are local variables at this point. So the recursive calls are not changing them.
The second recursive still has fixed with one character, and input is all the strings. In string is all input.
Well, input minus the last character, because you delete the last character.
Oh, that's what I was thinking, because if you don't delete it, it's just going to go into...
so you're always deleting. You delete the last character from in string. So in these two calls, the string is shorter.
Okay, now...
And every time you go, it becomes shorter and shorter. So there are going to be at most n nested calls. The total number of calls is 2 to the n, but there are only n nested calls.
Okay, yeah, I got it now. Thank you.
Right? The nested, there's only n nested calls.
Professor, do we have time to do an example with maybe like a really short string?
Unfortunately, well, okay, so maybe we can, maybe we'll do a short example. So let's just look at, sure, so let's look at ABC, string ABC, okay? So, so let's look at the first call. So I'll just say the in string is ABC and fixed is just the empty string. Okay, so now what is going to happen in this call is, okay, so this is unfortunate. Let me use XYZ instead, because I'm using C as a variable. Okay, so it's XYZ. Sorry about that. Okay, so let's go here now. Right, this is sort of the main logic. Okay, so what is the last character of in string? That's Z. So C is going to be Z here. We are going to delete the last character from in string. So in string is going to become XY. Now we make one recursive call. Now in that recursive call, the in string is XY. The fixed string is going to be Z. Let me just write out what's going to happen here, even though it doesn't get called initially. So the int string is xy, but the fixed string is still empty, right? I suppose I should have worked out an example earlier. Yes. Now let's look at what happens under this. So now the character C is going to be the last character of int string, which is y, and int string is going to become x. Remember, because you delete the last character. And then if you look at the two recursive calls, you'll have int string now becomes x, right, or the input, and the fixed string becomes yz. In the other call, the int string is still x, right, because when you delete the last character, then you use that as the input string, but the fixed string becomes z, right, because you don't change it, you keep it as is. That's what this call is doing. You just keep the fixed string as is. Okay, and then you continue this. So now, I'm sorry, the input string, so now C is going to become x, and the int string is going to become empty, because it's just going to delete that. So the int string is empty, and fixed is actually xyz, and xyz gets printed. And in this call, the int string is empty, and the fixed becomes yz, so yz gets printed, so on and so forth. So hopefully this makes things clear. Do you think you can work out the rest of this picture? So red is yes and green is no. Do you think you can work out the rest of this picture now? And is it making more? Yeah.
Just one quick question.
Yeah, sure.
If you reverse the two function calls, the recursive function calls, is that effectively reversing the print order of the list?
Exactly. It reverses the print order but doesn't do anything else, right? So it would then go from, this is in some sense, it's going from the longest to shortest, and it would flip that order. Exactly.
But it would not swap like the letters. Like if it was ABC, it wouldn't become, CBA.
No, it will still maintain the output. It just changes the order. Because if you look at the function calls, they don't actually change the input in any way. They don't change the arguments. It's just switching the order, because these calls are not going to change what these arguments mean.
That was a common question people had in chat.
I see. Yeah, it's not. So I recommend that you go and play around with this. Like, you can switch it in the code and see what happens, or you draw this picture. And I think if you draw this picture, it should make things really clear. So hopefully this is more clear now.
I have a question.
Sure.
So in the last part of the recursion code, it's just the last part of the graph. The last part.
Yes.
The last part of graph. Like if you have the base case, so it should be like enter another recursion call and then see the base case, or just like stay this recursion call and print. Because like I see the code you delete before, like after you enter the.
Right, but once this happens, this is a base case now, because when the input string is, okay, so the input string becomes empty in this call, you delete, and then you go in here, but then for this child call, the input string is now the same as the deleted input string, right? So this is.
So what they will enter another recursion call and
no,
see the basic case.
No, it's not going to enter another recursion call over here, because, sorry, maybe you didn't. The entire code first checks whether the input string is empty. That's the first check. So it is not going to enter another recursive call after that. Indeed, if you didn't have the base case here, then you would get an exception. So yeah, so just to be clear, there is no recursive call after this, right? So it's this, sorry, whatever mess I wrote over here, this is simply what happened locally inside this call.
I have a question.
Sure.
So just to make sure, everything to the left of the first call in the graph has to reach the base case before it moves on to the right.
Exactly.
Like the right of the first call?
Yes.
Oh, okay.
And moreover, every call on this side is going to have Z in the substring. And every call here is not going to have Z.
Oh, I see.
Right? Everything printed here has Z. Everything printed here doesn't have Z. You go here, everything printed here has YZ. And here, everything has Z but not Y. So on and so forth.
Oh, thank you so much.
Final questions before we move on? I'll just bring up. Again, like I will stress, like, you know, this takes some getting used to. The first time you see it, you'll have to spend some time on it, like drawing the box trace, like this sort of the tree of calls, which is also called a box trace diagram. It's worth drawing this out completely for this small example. And I think you will start understanding what's going on. And as you know, someone had suggested, switch the order of the calls and then see what happens. And if you work those two out, I think you will understand what's going on. You know, it might take you about an hour to sort of figure it out, but then you'll really get it. And once you get it, you'll understand the stack implementation. Like once you get this, go and you'll get the stack implementation. It'll take you a couple of hours to pour through the code, but it is totally worth it. And then after that, it'll be really clear. It should be quite clear. So at this point, I'm going to we're going to switch gears. We're going to actually now discuss a fairly different topic. And then we'll come back to more data structures, because I think it's important that we understand the notion of what's called asymptotic analysis of algorithms, which is probably one of your first introductions to the mathematics of computer science. It's a very important topic. This is what's called big O notation. And what we're going to do in the next couple of lectures is to understand what big O notation is. Once we understand that, then we'll appreciate a lot of the data structures a lot more, and then we'll come back to studying more complex data structures. So I want to start from a simple problem that many of you probably have already seen, which is sorting an array of ints, right? Very simple question. So A is an array of length n, and you want to sort it. What is the simplest sorting algorithm? Like simple reasonable sorting. I mean, you have to sort of implement one of these for homework 1 anyway.
Bubble sort.
There's bubble sort.
I think insert sort and bubble sort are the two easiest conceptually.
So I'm going to suggest that you're right. Insertion sort and bubble sort are some of the easiest. I think selection sort, which maybe you haven't heard it in those terms, is even easier, because what selection sort says is simply you find the minimum element in A and you put it at the beginning. Then you find the second minimum and then you put it at the second, in second place, so on and so forth. Right? So a really simplistic algorithm is simply find the minimum in A, swap with a of 0. Then you find the min in a1 going to n minus 1, right? Everything, because you know that a0 is the minimum. You swap with a1, so on and so forth. This is also called selection sort. It's a really simple algorithm. And it's actually, in my solution for the Twain assignment, I just implemented selection sort, and it's good enough. Okay, so this is a very simple algorithm. Let me actually write out the code for this algorithm just so that we have it in place. And again, I'm going to be somewhat careless with the specific syntax. So I'm just going to say for I going from 0 to n minus 1. Remember, n was the length of the array. So I'll just say the min is a of I. I'll start, and the min index is I. This is just initialization. This is just initializing. And now I'm going to go from, so now I want to, so this is just saying that here's I, and this is I. We need to find the minimum in whatever is in here and swap it with AI. We will assume that everything here is already sorted. That's what's happening in this loop. So we'll say for j going from I to n minus 1, we'll say if aj is less than, let's see if I'm getting my indices correct. Let's say if aj is less than the current min, then you just update the min, right? So you say the min is now equal to aj, and we say the min index is equal to j. And so we can end that loop. And once we're here, I'm just going to write this out, and I'll just say swap ai with a of the min index, and that's it. That's the code, right? This is how you can sort. So I just initialized. I said, okay, so I'm going to start at the ith position, find the minimum going from here to the end, right? This is finding the minimum. This finds the minimum. Find the minimum in a of I to n minus 1. So it just keeps tracking j, and you say if aj is less than the current minimum, then you just update the minimum, you swap, and then that's it. Okay, so any questions about this? This is selection sort. Okay. Now someone mentioned insertion sort, and insertion sort is also a fairly easy sorting algorithm. So insertion sort is kind of, you can think of it, it's sort of philosophically different. So selection sort says, so here's selection sort. It says this part is already sorted. And what you want to do is you want to find the minimum in here and put it at that position. Insertion sort says, now the problem with selection sort is that it kind of keeps going over this portion over and over again. What insertion sort does is says, well, this part is sorted. Let's just look at the next element. And let's just try to sort all of this part. Let's just sort everything on this side. Remember, selection sort doesn't sort everything on this side. It actually goes all the way, it finds a minimum and puts it. Insertion sort just says, well, let's just find out where this should go. And this is just done by, you keep swapping until it goes to the right position. Right? So this element just keeps swapping with its neighbors until it goes to the right position. So I just want to write this code down so that we have it, and then we'll come back to it later. So I'll say for I going from 0 to n minus 1, I'm going to initialize j to be I, and I'll say while j is greater than 0 and a of j minus 1 is greater than a of j. So this means that it's not sorted, right? If a of j minus 1 is bigger, if something in the right side, is the other way around. So if a of j minus 1 is actually larger, so that means that if this element was larger than this element, then you have to swap these. So we just swap aj minus 1 and aj. We do a j minus minus, and that's it. So this is insertion sort. So I just discussed two very simple sorting algorithms with you. Any questions about these? And so now a natural question that comes up is, I can come up with more sorting algorithms. So I have all these different methods of sorting. Which one should I choose? How do you determine the best algorithm for a problem? Now this is a very complicated question. Asymptotic analysis gives us one viewpoint by which we can address this question more formally. So actually I'll write this down over here. So we have these sorting algorithms. And so the question is how to compare or determine the efficiency of different algorithms for the same problem. And this is related to how to determine the best data structure for a task. And you could think of the best as the most efficient.
Efficiency refers to memory and computation time, right?
So good question. So what are we talking about? So you're right that efficiency typically refers to both memory and computational time. We are going to discuss running time. But space is also important. But in many of the instances that we see, the space is usually the same. Like if you look at both insertion, if you look at most of the sorting algorithms, not all, but many of them, the space is the same. It's the running time that usually is the distinguisher. But it's a very valid point. So I want to write down, how are we going to mathematically analyze this? Now the problem is, the time it takes to run could depend on the machine that you're running it on. A different like one computer may be faster or slower than the other. So it doesn't make sense to take two different algorithms and compare them on two different machines. You kind of have to compare them on the same machine. But on the other hand, the problem is, like, once we write down this algorithm, we don't really know how much time each individual step is going to take. So it's, how are we going to sort of mathematically describe this? So what we're going to do is we're going to say given, and I want to keep sorting in mind. So now that you have these sorting algorithms, you know the problem of sorting. Let's keep sorting in mind. So given an input x, I'm going to call it x. So think of x as the array, which we call a, but I want to call it little x, of size n. So this is the length of the array. Now the reason that I write x and n is, in general, this could be some other kind of input. It could be some other problem. Right now we're thinking of arrays and sorting. But you can apply this for any problem that we will work on. We can count the number of elementary operations that an algorithm A, so I'm going to use script A for the algorithm, that A performs on X. Okay, so A, for example, A could be selection sort. X is your array, and n is the length. But you could also think of A being searching in a list, X is the list, and n is the length. So X is the list and the element to be found. Right, so you have an algorithm that takes some input of some length and then does something. So when you're searching in a list, you get a list and you have an element that you want to find, and then you have some length. I'm going to call this quantity, so I'm going to write something down here. I'm going to call this the running time of A on X. What do I mean by elementary operations? So elementary operations, like if you look at this, every line is 1 or 2 or maybe 3 elementary operations, but it's some fixed number, right? So in the loop, you have a loop variable. So every time you increment the loop variable, that's one operation. This assignment is one operation. This check is one operation. This check is another operation. The AND is another operation. Swapping is, it's like 3 or 4 operations, right? Because you usually keep a temporary variable, you move things around. The decrement is one operation. So roughly speaking, it's like the number of lines, each line of code is like one, or you can think of it as some fixed number of operations. A function call is not an elementary operation because a function call is going to go somewhere else and then you're going to do operations over there. So in this case, each line is like one operation or maybe a few operations. The loops are where it gets complicated because the loop means that these operations are going to be performed many times. So you're trying to understand how many times are these operations going to be performed. That is what we call the running time of the algorithm. So we count the number of operations. We are not going to worry about whether one operation takes less than the other or not. So maybe a comparison is different from an assignment or an increment, but we'll just consider those together as the same. So we're just counting the number of individual operations. That is the running time of the algorithm on an input X. And I'm just going to write this as the running time subscript A on X. Okay, this is the number of elementary operations that is performed when you run an algorithm A on X. And if you want to make it concrete, think of selection sort on an array. Okay, so now I'm going to write down one more thing and then I'll open it up for questions. The worst case runtime. The worst case running time. Sometimes also referred to as the time complexity, is a function. It's a function that I'll say t sub a of n. So n is going to be an input size. And what it is it's a maximum over all inputs x, where x has size n, of the running time of the algorithm on X. So what this is saying is the worst case running time is actually a function, And the function says what is the worst or the maximum running time for any input of size n. That's what the function is. This is a function. It says, this function says what is the largest running time of the algorithm A, the algorithm is like a piece of code, of the algorithm A on an input of size n. Size, sometimes it also says length. This is the key definition. And this is called the worst case running time complexity. I'm going to pause here. I'm going to take any questions that you have on this before we proceed on to sort of comparing running times. Any questions? What this means?
Hey Sesh, could you go over the stuff on the right a little bit, like the max RT?
This?
Could you explain that one more time? Yeah,
sure.
I didn't catch it when you said it the first time. Sorry.
Okay, so that's fine. So what you have is, okay, let's sort of start from the basics, right? If you take any input, like an array, you can see how many operations that array performs, or the selection sort performs on the array. That's the running time on that input. Right? So it's the running time of the algorithm on the input. That's what this is. I'm going to sort of now say what is the worst running time, which is the largest running time for an input of a given length. So I can fix a length, n. I say, let me look at all possible inputs of length n. So like say all arrays of length n. And let me look at what is the largest running time for all inputs of length n. So that's the max over here. This is now a function of n, because for every input size, I can think of it as a thought experiment. Go over all inputs of length n and see which is the largest running time. This function is what is called the worst case running time. So the worst case running time of an algorithm, it's not a number, it's a function. And the function has this form. This is, I'm defining what this function is.
Someone asked a question I can't quite understand. They said, so would function calls take less time than any elementary operation?
No, function calls, so if there is a function call that is made, then you have to look at what are the elementary operations done by the function call. It's like you're tracking the number of elementary operations, where a function call itself could make tons of elementary operations.
From what I understood about the question, it wasn't about the function as a whole. It was actually calling the function in the stack to have the pointer, or I think the stack, like follow that function and map to that function. I think that was the question more so than all the functions, or all the elementary operations inside the function.
So you're saying like there's an elementary operation of like just retrieving it from the call stack or something like that, or retrieving the code?
I think that was more the question. Is
that you can think of that's also one elementary operation. It's one elementary operation to get the code. You could imagine that. But then within that function there are lots of elementary operations. So this is obviously a very complicated function. But now, we're sort of trying to simplify our way where we can now try to argue about these things. Any questions about this? This definition makes sense. So, okay. So now that I have these functions, let's say I have two algorithms to sort, selection sort and insertion sort. So I can look at how does TA of n behave versus T script P of n, where these are two different algorithms. So these are two different algorithms for the same task. Now, you know how to compare numbers. That's easy. But how do you compare functions? So the problem is, suppose I plot these functions. I'm plotting this versus the worst case runtime. This is the worst case runtime. And so maybe this is what TA event looks like. And this is what TB event looks like. So there are two different functions. Sometimes one is bigger, sometimes the other is bigger. So it doesn't really make sense to compare these. How do you say that one is bigger than the other? And so what we will do is we're going to employ calculus to actually be able to compare two different functions, even if they do, these weird things like this. So obviously, if there is a function down here, this is the C, you know that this is better. This is faster. And if there is a function up here, then this is much slower. But for functions like TA and TB, it's not clear which one is better than the other, at least just by looking at this picture. So the way that we resolve this problem, or the way this problem is resolved mathematically in computer science, is to look at what's called limiting or asymptotic behavior. So I'm going to write this out in three different ways, then I'm going to write the math down. What we actually compare, the way to think about this is, instead of comparing the functions themselves, we compare TA of n versus TB of n as n goes to infinity. So we're going to look at it, this is known as asymptotically, or also in the limit. Another way to think about this is, instead of comparing the functions, we actually compare the rates of growth. Now, one thing you can imagine is, for any sorting or any reasonable sort of algorithm, the problem is, as n goes to infinity, this also goes to infinity, because the larger your input is, the more your running time is going to be. And if you think about sorting, as your input becomes more and more, your running time is going to become more, so that if the input was, sort of infinite, then obviously the running time is also going to be infinite. So when n goes to infinity, everything becomes infinity. But on the other hand, calculus says that you can divide two things, two functions that are both going to infinity, but the limit can still give you some information. And so the way that we're going to compare these functions is, I should say that the definition that I'm using is not the precise definition of big O notation, but it is the one that I think is the easiest to make sense of. So consider the limit of n going to infinity of TA of n divided by TB of n, and let's assume the limit exists. Assume the limit exists. Because the limit might not necessarily exist in some cases, but let's not worry about that. Let's assume the limit exists. So you have these two functions. This is the running time of selection sort, the worst case runtime of selection sort. This is the worst case runtime of insertion sort. And we're trying to compare them. Now, what could happen to the limit? Now, we're going to break it up into three cases. So one is, the limit is 0. If the limit is 0, we're going to interpret this as saying TA of n is less than TB of n. This is like saying that if the limit is 0, then A is faster than B. This is like saying A is faster. Okay, I'm putting this in quotes because this isn't a formal statement. The second option is that the limit is a constant, which is not 0. So the limit is 1, 2, 3, root 5, pi, whatever have you. So it's some constant, some non-zero constant. In this case, we are going to interpret this as saying the algorithms are basically the same asymptotically. A is as fast as B, and vice versa. We're saying basically they're the same, running time wise. The other possibility is that the limit is infinite, in which case we will interpret this as saying TA is greater than TB. We'll say that A is slower when the limit is infinite. Okay? So this is how we're going to think about comparing two different functions. Any questions? All right. Now I'm going to go to big O notation. And I'm going to sort of generalize this and write this in more mathematical form. So let f and g be two functions from natural numbers to natural numbers. This means natural numbers. If the limit as n goes to infinity of f of n divided by g of n, if this is less than infinity, meaning that it could be 0 or it could be a constant, then we say that f of n is big O of g of n. And the way that this is usually said, it says it's big O of g of n. This is like saying that f is less than equal to g. If the limit as n goes to infinity, f of n divided by g of n is greater than 0, then we say f of n is big omega of g of n, or typically it's just said omega, because there's also something as little omega and little o. So usually it's big O, this is omega. It's like saying that f is greater than equal to g. And if the limit of f of n divided by g of n is c not equal to 0, then we say f of n is theta of g of n, and that's like saying that f is equal to g. Doesn't mean they're really equal, they're not the same function, but they're asymptotically the same. So now if you want to compare functions, you could do something like this. You could say f of n is going to be t of selection sort of n, and g of n, instead of comparing it with some other algorithm, we can say, what if g of n was n? Then which of these are going to happen? What if g of n was n squared? Then which of these are going to happen? So we can now try to compare selection sort with certain baseline easy to define functions. So instead of dealing with this complicated function, we can come up with simpler functions which we understand, like polynomials, and then use the O and omega and theta notation to basically say that it's the same as some simple function by taking the limit. So we can take the limit of t of n of selection sort divided by n, take the limit and see is this infinite or not. And if the limit is infinite, okay, then we know that actually t of n is larger than g of n. We can take the limit with n squared and see is this limit going to be infinite, is it going to be a constant, or is it going to be 0? This is under the assumption that these limits exist. There do exist functions where the limits don't exist, and in that case there is a definition that works, but I don't want to get into that definition. It isn't necessary for this course. But there is a definition when the limit does not exist. But the best, easiest way to think of it is in terms of these limits. So now let me poll you and start asking some questions. Question. So by the way, so if there's anything that you need to take away about big O notation, it's really this slide here. Like this is really what big O notation means. Okay, the technical definition says, there exists some n naught and a constant such that blah 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 happen. This is a simpler definition, although it only works if the limit exists. In many cases the limit does not exist, or in For certain kinds of functions, limits don't exist. You can still have this definition though. But for all the cases we're going to be discussing in this course, and probably you will see throughout your CS career, you're not going to see the limit. You'll see a situation where the limit exists. So let me ask my first question. I'll say, can f be O of g and f be big omega of g? And say yes, and g is no. Okay, so let me launch the poll. Here are your definitions.
So R is yes and G
yes,
is
R
no?
is yes and G is no. Okay, so I think most of you got the correct answer. The answer is yes. I mean, f could be equal to g, in which case the limit would be 1, and 1 is less than infinity, so it's O. 1 is greater than 0, so it's omega. Indeed, in this case, in any situation where f is theta of g, it means both of these are happening. So actually, f is theta of g means f is O of g and f is omega of g. Right? When both of these hold, then f is theta of g. That's exactly what this is saying, right? Because it says if the limit exists and the limit is a constant, that means it's greater than 0, and the limit is obviously less than infinity because it's a constant. So this can happen. Okay. Question. Is n O of 2n plus 3? Again, the red is yes, and G is no. Remember, just take the limit. Take the limit, and you'll see the answer. Take the limit and you will see the answer.
I have a quick question.
Yes.
Do we essentially just use L'Hopital's rule on that?
You can, yeah, sure. Yes, you can use L'Hopital's rule or any other way of computing the limit.
Okay.
Someone said they don't quite understand the question.
Like, is this statement true or not? Or is that itself the confusion? Like, this is, like, if this happens, then we say
On is equal to On 2n plus 3?
sorry? Is
On is equal to On 2 plus 3?
No, it's n O of 2n plus 3. Is n big O of 2n plus 3? Okay, so most of you seem to have got it right, but I think there are some people who are still confused. So let me write this down. So this is the function n divided by 2n plus 3. You take the limit as n goes to infinity, and if you apply your calculus, you'll say the limit is a half. And because you could divide this by n, you can divide by n over here. You get 1 divided by 2 plus 3 over n. As n goes to infinity, this becomes a half. And half is less than infinity, so this is O. Half is the limit is less than infinity. So it's O. Okay, now question. Is n O of n divided by 2 plus 3? And again, the answers are yes or no. Just going to relaunch the poll. So is n big O of n over 2 plus 3?
Professor, can
Yes.
I ask a question about
Sure.
the second
Sure.
second one that you just talked about?
Yes, this one or this one?
Second question. Yeah,
Yes.
when the result is 1.5, shouldn't that just be the theta because it's a constant?
Good question. So it is theta, but it's also O. Remember, so if
Because
it's less,
it's smaller or equal to, right?
I'm sorry, because it's smaller or equal to, exactly. You're absolutely
Okay, thank
right that it is also theta. So you can have both of these be true, because if it's less than infinity and a constant, then it would be theta as well as O. So good point. So when it's theta, it's actually both O and omega. And you're absolutely right that this is also theta, but this statement by itself is true, that it's O. Good point. Okay, so in this case also the answer is yes, and that's because the limit as n goes to infinity of n divided by n over 2 plus 3, this limit is 2, and 2 is less than infinity, so it's O. Okay. Now let me ask you another question. Is 5n cubed plus 10n O of n square? Okay, again your options are yes, and the green is no, so I'm just going to relaunch the poll. Now tell me, is it O or not? Okay, so the answer is no, which most of you got. And that's because if you take the limit as n goes to infinity of 5n cubed plus 10n divided by n squared, then this limit is infinity, which is not less than infinity. So you may have observed that when you take this limit, this part doesn't matter. And this constant doesn't matter either. What matters is the fact that this is n cubed and this is n squared. And the cube dominates the square, and therefore the limit is infinity, so it's not O. Okay, ask a few more. Is 2n plus 3 O of n squared? So is 2n plus 3 O of n squared? So this one has more people confused. The answer seems to be 60-40 in one direction. So the answer in this case is yes, and that's because if you take the limit as n goes to infinity of 2n plus 3 divided by n squared, you get 0, and 0 is less than infinity. So n is O of n squared, but 2n plus 3 is not theta of n squared. It's not theta, but it's O, right? Because the limit is 0. It's not a non-zero constant. Okay. Okay, good. Now I'm going to ask you a more challenging question. Is log base 2 of n O of n? Yes or no? Right, so is log base 2 of n O of n? So there's more divergence for this question. Or actually, again, it's going 60-40. So the answer is yes, because the limit as n goes to infinity of log base 2 of n divided by n, this limit is 0. You can apply L'Hopital's rule here. If you wondered why calculus is a prerequisite for these courses, it's precisely for this reason, is to understand these definitions. Okay, let me ask you now, is log base 2 of n O of square root n? Yes or no? Let me relaunch the poll. So is log base 2 of n O of square root of n? So again, sort of 60-40 here. Well, actually, it's almost closer to 50-50. So again, the answer is yes, again by L'Hopital's rule. So I'd recommend that you go and work this out. By L'Hopital's rule, you'll again get the same result, that even if you put a square root n there, the limit is 0. So the important thing is if you have some kind of running time, some function of the form, let's say 8n squared plus 5n plus 100, so then you say t of n is basically O of n squared. So you ignore this part and this part. This is called a lower order term, and this is a leading constant. The asymptotics of this function are determined by the highest degree. And so you say that basically in this case T(n) is actually theta of n square. So we ignore the leading constant and we ignore the lower order term. And that's what happens when we do asymptotic analysis. We're saying that in the limit, this part doesn't matter, and the constant also doesn't matter when we're understanding rates of growth. And so I'll end here, and when we come next time, we'll talk more about big O notation and how we use this to describe algorithms. We've covered a lot of ground today, so I recommend that you go and look at the the recursive code and understand how to implement it through stacks, and also read over the definitions of big O, because we're going to be heavily using that in this course.